All right, we're going to get started. All right, thank you for coming to the January event. Happy to have Charles here. He's going to be doing a workshop on applied supervised machine learning for cybersecurity. So very trendy topics, right? Cybersecurity, machine learning. So that's why the turnout's really great. Thanks everyone for coming. Before we get started, I'd like to thank the sponsors, and I'll just go over some of the future events. Once again, there's a lot of pizza in the back. Eat the pizza. Brownies are awesome. So Varen Technologies is a large defense contractor. They've been supporting the meetup for several years now. So if you're interested in learning more about their company, just come up to me and I'll introduce you. Clarity Business Solutions. I don't think anyone from Clarity is here. Right. So Clarity Business Solutions is another defense contractor doing data science, software engineering, system engineering, smaller company. So if you're interested in learning more, you can come talk to me. Next Century, we're recently acquired by CACI, so I think there's some folks here from that company. Larger company, but also doing a lot of interesting things, both in the area and other Virginia, other areas, data science, system engineering. If you're interested, come and talk to me and I'll introduce you. Miner and Cash is not a defense contracting company, but they're data science consultant, so they do a lot of work up and down the coast. They do a lot of consulting. If you're interested in learning about their opportunities, come talk to me and I'll let you or introduce you. This mic sounds weird. Is it okay? Can you guys hear in the back? So Ares Ventures is my company. We're a defense contractor. If you'd like to talk to them, talk to me and I'll introduce you. Yeah. Loyola, do you want to introduce yourself, Chris?
Yes, hi, I'm Chris Morrell. I'm the director of our data science program. Welcome to Loyola. Yeah, 3 or 4 times a year you come here, right?
Yeah. Mm-hmm.
So, great to see you all here.
Thank you.
Yeah, Loyola's been great. They've hosted us for many times, and they have a data science program. They're really trying to get involved in the community. And there's actually an upcoming data science panel that I think is available to RSVP now, and there's going to be a lot of really great speakers, like Dr. Harvey from the NSA, so he's going to be speaking, and there's some other phenomenal speakers. So if you're interested, go check it out, the Loyola website. All right, quick announcements. So February's event's already posted. It's on Delta Lakes. It's from the guys at Databricks, so that's going to be at APL. In March, it's going to be one of the data scientists, visualization, data journalist individuals from the Baltimore Sun, so that'll be interesting. And then further out in the month, further out in the year, we're gonna have someone come and speak on Amazon web racers, so like the autonomous vehicles that you can program. We have speakers that are going to come talk about potentially cryptocurrency. So the whole next 6 months are lined up, so it should be pretty exciting. We have a newsletter. If you're interested, you can sign up at the URL here. Not shocking, all sponsors are hiring. So if you're interested in work, please talk to me and I'll introduce you. If you have any experience doing conferences, I would be very interested in talking to you. I'm looking to do a conference, and I could use a lot of help. So if you're interested, talk to me. And if you're interested in speaking or sponsoring, also talk to me. All right. So Charles is a data scientist. He's a manager at, where are you manager? I do a lot of these events, and I forget. Sorry about that. But more importantly, he's also the CEO of GTK Cyber, so he does a lot of cyber training. He's an expert in the field, data science, doing stuff with cyber. So I think it's going to be very interesting. I think you're going to enjoy the talk. Last thing I have is we have a ton of books that I'm going to give away. I have a ton of shirts. The way that I do it is that if you ask a question, you come up at the end, and then whoever comes up, I give you an opportunity to take something. So ask your questions and then come up to the end. Okay? All right. With that, I'm going to hand it over.
All right, good evening, everybody. Thank you very much for coming. My name is Charles Givre, and yeah, you heard the intro about me. I work at JPMorgan Chase. I'm a product owner in our cybersecurity group right now. Prior to that, I'm also the PMC Chair for the Apache Drill project, which, interestingly enough, I'm actually not talking about tonight. Let's see, before that I was at Booz Allen for 7 years, and then I worked at the CIA for a while, and I went to the University of Arizona and Brandeis. So that's my story. I'm just kind of curious. But before I continue, I definitely want to thank Jason and for inviting me, and our sponsors, and also Loyola University for hosting. Can I just see a show of hands? Who here has a job where you consider yourself to be a data scientist or some sort of data science-y job in your title? Okay. How about software developer or software engineer? Okay. All right. Who works in cybersecurity? All right. And who codes in some language? All right. Okay. All right. So before I kind of get started, I just want to say how I crafted this presentation. I wasn't when Jason initially asked me to do this, I thought, okay, I'll kind of pull material that I thought. My assumption was that the audience would be kind of more familiar with cybersecurity and less familiar with data science stuff. So what my game plan for tonight is, I'm going to kind of give a brief introduction to machine learning. Then I'm going to talk about how it's applied to cybersecurity, and then we'll walk through some use cases and some techniques that you can actually use. And there's a Jupyter notebook that if you brought your laptop, you can try out and experiment with some of this stuff. So sound good?
Good.
All right. My expectations, I strongly encourage you, please, 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 if you have a question, ask it. Someone else is probably wondering the same thing, so don't be shy. I do not stand on ceremony on that, so please raise your hand, shout it out, whatever. I would strongly encourage you to try out the coding examples as we're doing them. Try them out, see if they work, see if they break, whatever. Like, you'll learn a lot more from that. There is a GitHub repo, which I'll share in a second. There is a worksheet, which is blank, and then there is an answer sheet as well, so try to do the exercise without looking at the answers. I mean, I'm not going to take points off if you look at the answers, but, you know. And, I didn't set up Slack now, so sorry. Okay. All right. This is the GitHub repo, so it's github.com/dataworksmd_workshop. I would encourage you to please grab this now. The slide deck is in there, as well as some other reference materials that might be useful. So if you're not familiar hopefully everybody knows how to do this. You can just go to this URL and just download the files if you don't want to deal with the whole like Git version control stuff. But if you do, you can fork it and clone it and all that. I'll just leave this up for a second. We've got this really awesome setup here. Like, I just have to say, no one here works for Apple, right? Okay. I actually really like Apple, but I'm really pissed at them that I now have to use like 3 adapters to connect to this monitor. Yeah. My old MacBook, sorry, now I'm on a rant. My old MacBook was freaking awesome. Like, it just worked. You know, I had a dock for it. I hooked up to my 2 monitors. This one draws so much power that it can't power my monitor. Like, when I have like my video conference stuff, it like sucks the battery down and doesn't draw enough power to charge. Anyway, all right, end rant. Okay, one more shameless plug before we get into the material. My company, GTK Cyber, we're doing a class in May, the week of May 4th. The first day of it is like a data science literacy. This is more of like for managers, and then we're doing a 4-day version of the course that you're going to experience now. But it's obviously a lot more in depth. Goes through the whole data science as applied to cybersecurity, and yeah, good class. Definitely encourage you to. Okay, all right.
Well, let's go back for a second.
Oh, okay. All right.
I see the date. I don't see the place.
It's
Location.
It's okay. So if you go to the link there, it has it. It's in this place, Phoenix Classroom.
Okay, so it's not going to be in San Francisco, for instance.
No, it will not be in San Francisco.
Actually, I forgot to also say that we're going to be raffling a ticket.
Okay.
So Charles was kind to give us a ticket for the 4-day course. So check your email. I'll send it out through various means. But then in the next week or so, there'll be like a little raffle. So then you can win. Thanks. Actually, there's also a raffle right now for a pass to the Software Architecture Conference up in O'Reilly, so it's like a free bronze pass if you go to the website. That's it. Sorry.
All right, yeah, so if you don't have enough, if you haven't had enough of my bad jokes by tonight, you can come for 4 more days of it in May. All right, so what I'm going to do first is I want to start out by kind of introducing the topic of machine learning and define it and set the expectation there. So I've seen a bunch of definitions for it. This is one I definitely like. It's the machine learning is the science of getting computers to act without explicitly being programmed. This is the part. Oh shit, is this not working? I'm not having a good tech day. All right. Well, this definition I just put up there because I hate it so much. I don't really know what that means, but okay. This was from Wikipedia, and I think this is actually very well. The key phrases here that I want to highlight are making predictions from data and not following strictly static programming instruction. This is really what makes machine learning so valuable in the cybersecurity context. Our adversaries are getting more and more sophisticated, data volumes are growing exponentially, and it's not really possible to manually defeat all of the or mitigate all the threats that exist to a large enterprise. And so we have to be one step ahead of our adversary, and machine learning is one technique that can enable us to do that. Now, a great example of how machine learning has been applied to cybersecurity is spam. Now, I will date myself. The first email I ever had was not from AOL or Gmail because those did not exist. It was from a local ISP from the sticks in Arizona. And when I first got it, it was great, and then it lasted for about 6 months. And then someone invented spam, and all of a sudden my email was just deluged with garbage. So what happened kind of in the ISP world was ISPs started to figure this out, and it was really a nuisance for them. And they started building filters, and they would look for words like Rolex and Viagra and whatever. And so they started to filter that stuff out. And then they would discover that this was coming from shady IP addresses, so they would block them, they would manually do this. So what happened? The spammers adapted. And they came up with new forms of spam to defeat this. And this is really, in a way, it's very illustrative of how machine learning can be used to solve a very serious cybersecurity problem. So what happened was, as I mentioned in the beginning, the ISPs and email providers, they would use blacklists. Basically, they would encode real-world human knowledge to defeat spam. So they would, again, looking for keywords, they would look for suspicious IPs, whatever. Over time, they started to use a machine learning technique called naive Bayesian classifiers. And this was proven to be very, very effective at identifying spam. Now, what the major email providers use, they use deep learning to defeat spam. But I would argue that spam is largely been defeated by machine learning. I mean, yes, every one of us gets an occasional spam in our email, but if you think about how much is spam versus how much actually gets through the filters, it's a really low amount. And if spam, as crazy as it sounds, does remain one of the major attack vectors even to this day. So, or phishing email, but some variety of this, unwanted email is basically is still a very serious threat. Okay, so just kind of to define some of the buzzwords that are out there, or limit them at least. We have this notion of AI, which is defined loosely as any kind of behavior that mimics human behavior, any technique which enables computers to mimic human behavior. Within that, machine learning is a subset of that kind of uses statistical methods that improve with experience. And then, if you're not familiar with this, deep learning is a subset of machine learning that uses deep neural networks. I'm really not going to get into deep learning today. I'm going to kind of talk peripherally around it. And it's very cool. And if you haven't messed with it yet, you probably should take a look at it. I saw this quote, and I just had to put it in a slide deck, but there's so much hype and, frankly, BS that goes into machine learning and what's interesting to me is just a lot of the math behind it is hundreds of years old, and so I personally love doing this when vendors come to pitch stuff to us, pitch machine learning products to us, and they start telling you about how they're using some advanced machine learning, and you're like, oh, okay, that's interesting. and you just kind of let them go for a while, and you find out that their whole product is like some linear regression algorithm or something like that. But anyway. Okay, so there are two broad families of machine learning. There is supervised and unsupervised. Supervised learning is where you have where you start out with a data set where you kind of quote unquote know the answers. Unsupervised is when you don't, and so when you do not start with that, and you're kind of limited in terms of what you can do with unsupervised learning. Now, the security world, many of the problems, we do have a lot of data. But as I'll explain later, one of the big challenges in cybersecurity is that it's often difficult to get balanced data sets. And if you think, if you kind of consider the case of, say, predicting credit card fraud, not really cybersecurity, but similar-ish. If you're a bank and you want to build a model to identify credit card fraud, you will have hundreds of millions of legitimate credit card transactions, and hopefully very few fraudulent transactions. But the problem is actually a little bit more than that. You may have tons and tons of like what you think are mostly legitimate, and then you'll have known fraud. So it's like you'll have tons of what you're mostly sure that it's legit, and then you'll have a lot that's some that are not. So you have the balance issue, and then there's the certainty issue there. Anyway, okay. Now, within the machine learning world, there are these different problem types, and what the predominant problem type in cybersecurity is classification. This is a supervised learning technique, and this is when you are assigning a class to an unknown observation. And if you think about this, things like predicting whether or not a given email is spam or not, that's the two classes would be like legit or not. If you're trying to identify SQL injection, again, is it SQL injection or not? So a lot of cybersecurity problems map very well to binary classification problems. Making sense so far? Everyone still awake? Okay, all right. I'm not really going to get into regression other than to say it's predicting a continuous value based on an observation. And this is a supervised technique as well. There are not as many opportunities to use this in cybersecurity, though they do exist. But you will find, and I have a list coming up of various cybersecurity machine learning problems, and you'll see that like 90% of them are either clustering or classification problems. Now, I tried to color code these, so the blue ones there are supervised, the green ones are unsupervised. But the clustering is when you're looking for kind of groupings within a data set. This can be used for anomaly detection, which, as you might imagine, is a big use of machine learning in cybersecurity. And it has a lot of other kind of applications. One of them, an interesting one I saw, a guy I work with was, one of the challenges in large enterprises can be identifying what a particular server does, which sounds kind of funny. So he built a cluster that, based on kind of nearest, like what are similar machines to this doing, and then like, okay, we can guess this is a Linux server, or we can guess this is a printer, or whatever. So it was an interesting way of doing it. Yeah, okay. And finally, dimensionality reduction. This is kind of taking a large amount of variables and reducing it down without losing the information. So what problem is it are you trying to, so when you're doing this, the first thing you kind of want to ask yourself is, do you have labeled data? If you do, you have basically all of these options available to you. You can do supervised learning, you can do unsupervised, and you're golden. If you don't have labeled data, the next question you might want to ask yourself is whether or not you can come up with some creative way of labeling that data. How many people, let me just ask, what happens when you use some service that uses Google authentication and it maybe doesn't quite like you? What happens? Yeah, you get the CAPTCHA. Then what happens? What does it do?
Tell us which pictures are bridges.
Yes. Why do you think it might be doing that?
You're classifying.
Huh?
You're classifying.
Yes.
Doing the work for them.
You are helping them create a labeled data set of images by clicking on them and saying, yes, this is a bridge, this is a bridge, this is a crosswalk, this is a fire hydrant. So they came up with a very creative way of enlisting all of you to assist with creating this data set. So thank you. On behalf of Google, thank you. Okay. I've seen others. That's kind of the most common, the most, like, the example that always sticks in my mind. But I've seen other ways that people have come up with to creatively label data, unlabeled data sets. If you can come up with one, it's very valuable. Now, if you can't label it, then you're stuck with doing unsupervised techniques. So this would be clustering, making recommendation engines. I'm not going to get into that today because that's kind of outside the scope of what I'm going to talk about. And anyway, so I'm just going to leave it at that. Okay, and finally, I'm sure anybody who's done machine learning kind of chuckles a little bit when people start talking about AI taking over the world. Yeah. All right, so applications to security. There are many, many applications of machine learning to cybersecurity, and interestingly enough, I started teaching this about 5 or 6 years ago. I taught a class at BlackHat, and I think the first year we did it, we had 30 people in it. Last year we had almost 100. So there's definitely a growing interest in, and a growing recognition that machine learning can be successfully applied to solve cybersecurity problems. And there are many of them. So if you are interested in learning machine learning and you work, if you work in cybersecurity, this is definitely something you should learn because it's definitely a growth industry. Anyway, one example of regression might be predicting server capacity or network bandwidth usage or something like that. Again, there's not a whole lot of this kind of stuff, but what this can be done, this technique could be used for is to detect abnormal activity in either anything where there's kind of like a signal or something like that. Clustering as well, it can be used for anomaly detection, and a lot of security problems can be broken down as an anomaly detection problem, like detecting distributed attacks, things like that. Those kinds of things can be, you can tackle them with anomaly detection techniques. Network-based intrusion, so this would be like pulling features from raw network traffic and identifying intrusions, identifying anomalous behavior, doing, I guess user behavior analysis, these kinds of things. You can do a lot with machine learning there. There has been, in the last few years, a lot of really, really interesting work done with malware classification and machine learning. A guy I worked with actually 2 people I worked with at Booz Allen wrote some really interesting papers about applying deep learning to identifying malware. And so essentially what they did was they would write classifiers where they would take an unknown executable file, feed it through a machine learning model, and it could predict kind of what family of malware this unknown software was. So it's a very, very interesting area. Now, in the last year, there's also been a lot of kind of interesting stuff with respect to a technique called adversarial networks. And people have created malware that can basically fight the antivirus and detection scheme. So they've been able to kind of create these models that will subtly modify existing malware so it will not be detected by existing malware detection schemes. All right. So with that said, so we have this list here of various other applications. The first example here is the one I'm going to highlight and use in this workshop, and that is domain generating algorithm detection. Who knows what this is? Okay, all right, one person. So, okay, just kind of really quickly, when a miscreant wants to create a botnet or do something evil, one of the things one technique they will use is they will plant some sort of malware on a server. Now that malware, they'll want to control that, so that malware has to like connect back out. So in the early days, what they would do is they would just hard code an IP or domain or something like that, and then that malware would then just connect out via that way. However, that's easy for a sysadmin to just block that once they find that it's there. So more sophisticated malware, what they did was they would create these algorithms that used a random seed that would generate domains that looked like just random gibberish. But this algorithm was synced with a command and control server. So these malware, these programs would get implanted on some device. They would generate 50 or 100, thousands of these domains per day, but it would be synchronized with a command and control server. And so it became very, very difficult to block these because you couldn't just block one thing. And there's a really interesting book about, I'm totally drawing a blank on this, and it will hit me probably right when I get to my car. But yes, sir.
And each domain has separate IPs?
Well, it's, I mean, I was supposed to, I suppose so. I'm not sure exactly how that end of it worked. But from the,
I think the book is The Worm.
yes, thank you.
It's a really
Yes.
good one, too.
That is an awesome book, yeah. It talks about how this malware had the potential to take down a whole DNS system, and how like these guys fought back against it. Really interesting. Anyway, if you find this stuff on your network, it's almost always bad. There's like no legitimate use for this, and it's a really good use case for how machine learning can be used in a defensive capability, and it's also very easy to understand. So we'll talk more about that. Malicious URL detection, kind of a variation on that. This would be like, how do you distinguish a malicious URL from a legitimate one? Beaconing detection, so oftentimes when malware gets on a server, it will have to like phone home at regular intervals, and so being able to detect that out of like the wash of network traffic can be is a very useful thing. And again, people who design malware aren't stupid. They'll put jitter in the pingback times and things like that to make it challenging. So being able to find that kind of stuff is a good use of machine learning. And you guys can all read this stuff, so I won't read the whole list to you. Now, machine learning can also be used as part of threat hunting, and it basically can be used as a very sophisticated filter. And when you are doing threat hunting, you start out with a monumental amount of data, and you have to get that down to that tiny tip of the triangle down there at the bottom to find that potential bad. And so machine learning can really help identify anomalies. Not all anomalies are bad, but can find things that are interesting, and then by repeatedly applying machine learning to that, you can really whittle that down to find the interesting stuff a lot quicker. All right. So next, what I'm going to do is, I'm a big believer in learning processes, so I'm going to quickly go through kind of the process of how you develop a machine learning model, and then So the first step is gathering and cleaning your data. With security, this is a major challenge. Security data often comes in a lot of flavors. You'll get log files, you'll get XML, you'll get PCAP, which is raw network traffic, you get all kinds of stuff like this. And it is a big challenge. Oh, and you also usually, especially if you're doing this at any serious level, you also get like terabytes of it. So you have to like kind of have good ways of dealing with large amounts of data. Once you've done that, then there's the next step, which is feature engineering and extracting the features. We'll talk more about that step. But that's when you, like oftentimes when you can't just feed the raw data into a machine learning model. You have to extract attributes of it, and that's a really key part of building a machine learning model. Hang on one second. I didn't turn on my thing here properly. Sorry. Annoying.
Just for the back of the room, what was the name of that book?
Worm.
Worm, thank you.
All right, well, okay. So once you've done that, then once you have extracted your features, the next logical step you'll have to do is oftentimes you'll have to apply a bunch of different transformations to your features to prepare them for machine learning. Again, this kind of stuff is far more than I could possibly teach in an hour, and I talk fast, so it's a lot. Once you've done all that, your data is now ready for building a model, and this is kind of the easy part. So the next step is you would take your data, you split it into a training and a testing set. You use the training data to train your model, and then you use the testing set to make predictions. And you then compare those predictions with the predictions and with the answers in the testing data, and you can get a sense of how well your model is actually working. Now, unsupervised learning is largely the same in terms of all the data preparation that you have to do, but there's no training and testing. The way you evaluate those models is quite different, and you can't really prove that they work in the same way that you can with a supervised model. Okay, any questions about any of that? Yes, sir.
Just one, from cybersecurity perspective, the data you're talking about is just network traffic?
It can be anything. It can be network traffic, it can be log files, it can be, so the example that I'm going to walk you through, the DGA detection. You might, your data source might be like raw firewall logs. or it might be DNS records or something like that. So there's a lot of different, it's very rarely will you get something like a clean spreadsheet that you just.
Okay, but I guess my question would be, you're going to build your model, so what are you going to try to do inference on?
What are you trying to predict, or what?
No, in other words, you're going to build the model, right?
Yeah.
And then train it.
Yes.
Then you're going to try to run inference against something.
So, okay, so what you would do, and I mean, if I'm understanding what you're asking me, is like, you would then, you build your model, you build the code to, turn that raw data into something that the machine learning model can read. Once you have that pipeline of steps, you can then use that to feed new data into it and make predictions from it.
Yes, and what I'm saying is that new data that you're
Yes.
feeding in,
Yeah.
that you're doing inference on. I'm just trying to understand the difference between your model and like, smart firewall.
So I mean, it's largely the same. I mean, smart firewalls often use some form of machine learning, so it's largely the same.
Okay, so you're doing inference
Yeah.
on live traffic.
Yep.
Okay.
Yep. I mean, it's not. Let me clear. It's not always live traffic. Sometimes you'll have static examples, but yeah.
As
So-
a follow-on from that question, what would you see as the most valuable sources of data to be put into this?
Most valuable sources of data. So that largely depends on what you're trying to do. But I've found that so the work that I've done has largely been in like network defense. So that kind of activity, proxy logs and DNS logs are like your gold mine. The next most valuable, like if you're doing I'm working with some guys right now, they're doing incident response. The next, like for them, PCAT files are absolutely most valuable. But it's largely driven by what it is you're trying to do. So, a question in the back?
Yeah, I have a question about transfer learning. So the conversation of supervised versus unsupervised, if you have an existing model that you're pulling layers from to apply to something new, do you have to know that existing model? Do you have to know if it was supervised or unsupervised in order to incorporate it into?
So the question is let me come back to that, and I'll yes. Okay. Sorry. Good question. Okay, so when you're doing this, the first thing I would definitely advocate doing is defining what it is you're actually trying to do. What is it that you're trying to solve for? Oops. A big issue with security models also that you would want to think about is how are you defining success? How do you know if your model is good enough? There are a lot of constraints that again, depending on what industry you're in, you might not think about otherwise. One example of this is like, if you were building a model, is 99.9% accuracy good enough? Well, okay, so let's say this model sends some alert to a SOC analyst or an incident responder that's going to go and investigate that. Okay, let's say you're putting 10 million records through this model a day. Okay, so how many alerts is that, how many false alerts is that analyst going to get? I call this the piss off the SOC metric. And in all seriousness, it's something you kind of want to think about. And it's one thing I know when vendors come approach us with their whiz-bang solutions, it's something I will always ask is, how good does it perform, and what are the false classification rates and all those kinds of things, because you don't want to annoy the human responders who are going to get the results of this, because then they stop trusting them. So again, how do you define the success? Make sure you have a good definition that works for you. Once you've done that, the next thing you're going to do, and this kind of gets to the questions that people have been asking, is choosing data sources. And you'll want to ask questions like, what data is available? Is it enough? It probably isn't. Is the data reliable, clean, and consistent? I'll answer that one for you. It also probably isn't. And what other data is available? One of the things that I find, when you're dealing with like live network collection devices and things like that, there is a false impression that these devices will always generate correct data. They will not. Someone will trip over the power cord, or take a server down and not tell anyone. All sorts of stuff like this will happen, and you just have to kind of expect that that's going to happen. So, be aware of that. And of course, there's other things you want to think about, like policies, legal constraints, biases in your data. Latency is a big one. With security models, you want to think there are some modeling techniques that will not work with large amounts of data. And so consider again the case of credit card fraud. If you build a model that takes 10 minutes to make a prediction, that's not useful. Because no one's going to want to sit there and swipe their credit card and wait 10 minutes for it to be approved. So you'll want to kind of think like when you're starting a problem out, or when you're starting to work on a problem using machine learning, you'll want to kind of think about whether or not latency is like matters and data size. Okay. All right. So I'm just going to
Hey,
kind of
Charles.
go quick. Yes.
I had a question. So with the biases, I know like people talk about biases in other applications like loans, but what would be the biases in cybersecurity?
Okay, what are the biases? The question is, what are biases in cybersecurity? I'm trying to think of a good example of this. Oftentimes, I think it relates to kind of what I would call like sampling data, like basically being unaware of your environment. And okay, so I worked on a project where we were building a model to identify, okay, so just to set the setting, a place where I used to work, anytime a sysadmin logged into a production system to do any work using a root level access, their sessions were audited. So a human had to like go and look at everything that they were doing. So what we were trying to do was we were trying to reduce the amount of human effort involved in that. So they had a proprietary tool that would like cut, that would basically say, okay, 70% of these are okay. So leave these 30%, which was still a lot of work for people to do. So I was part of an effort to make a model that would really cut that down. So the first efforts to do that were like incredibly successful, or at least they appeared to be. After digging into the model, what we found was that it was just not really working very well, and the reason why was because there were so few actual incidents that merited investigation. So the bias was we had a highly imbalanced data set, and so it was very difficult to actually find indications of actual malicious activity. So that might be one, that's kind of one example. I think in general, in cybersecurity, one of the causes of biases are just highly imbalanced data sets. Yes, sir.
So one of the issues I have is with machine learning empiricism washing.
Would you mind just standing up and really speaking up?
Yeah, one of the issues I've had with machine learning is empiricism washing, and I think it's kind of hitting upon it with the question of what are you trying to answer. People will build models and say, hey, it does this, it's maybe correlative, but not positive. How do you, the modeling aspect, I think, helps deal with that a lot. How do you go and structure how you think about models, what's a good model, what's a bad model, how do you apply models to your data? The rest of this, machine learning, is pretty relevant.
Okay, so you're asking how do you know if the model's any good? Is that kind of...
Well, how do you pick the right model? How do you know it's the right one?
Okay, let me come back to that because I'm going to show you some techniques for doing that. And if I don't, come talk to me afterwards. Yes, sir.
When it comes to building a robust model, you obviously need, like, there's a certain amount of data that you need as your minimum quantity of data.
Sure.
Can you talk to sort of some of the intuitions that you might have as to determining if you have enough data without actually going through the whole process of building
Sure.
a model and testing it?
So, okay, usually with, in my experience with security, having enough data is not the issue. It's usually like I mean, you can, there's a ton of data coming off of any wire that I've ever had to mess with. So it's not usually a question of the volume of it, but it's a question of kind of like getting good stuff out of that. So that is a much more difficult problem. So in the example, like I said, of finding malicious admin sessions, we had thousands of admin sessions, but of that, we probably had like 30 or 40 incidents. So that was a real problem. In that case, you just kind of have to do the best you can. And I'll show you a technique for dealing with imbalanced data sets, but it really kind of depends on, yeah, usually that's the issue, not so much like the sheer volume of data. The other thing is, of course, the actual data quality, and there's really no way of like kind of, basically the only way that I know of to really determine how good your data is from a quality perspective is just a lot of exploratory data analysis. I will proudly admit one of my spectacular failures was I was working with data from some, I was doing an experiment with some automotive data, and I was trying to build this model that could identify like whether or not the regular driver of a car was actually driving the vehicle. So I gathered all this data and I was doing all this stuff and it was looking really good. And I don't remember exactly how I discovered this, but basically I discovered that like half of my data set was entirely corrupt. And it is what it is. But the way I found it was just a lot of exploratory data analysis. So that's kind of one skill that I'm a big believer in, the kind of those core foundation skills like getting data, doing that exploratory data analysis, visualization. The better you are at those things, the faster you are. You can find those kinds of things, and that will prevent you from being successful.
So which exploratory data methods do you use?
Oh man, all right. Which exploratory data? Okay.
I mean the most.
The most? Depending on what kind of data I'm looking at, I'm a big believer in visualizing stuff. If I'm using pandas, I will just go through all the auto summarization stuff just to look for anything weird. I mean, the things I want to know first off is like, are the columns populated at all? Because oftentimes, like if you have a very wide data set, you may find that certain columns are just not populated or not populated with the correct things. Anyway, that's my 30-second version. Okay. Yeah, I'm gonna start talking like the micro machines guy. Okay, feature engineering. You can't put a shark through a machine learning model. You have to find attributes of that object. So let's say you're trying to classify marine life. What you got to do is you got to find things that describe that. So in this case, I pick color, the fins, and whether or not it's a predator. Now, those features do not adequately describe this, because if we put this up there, that basically describes the dolphin as well. So the key when you're doing a machine learning project is to find features that adequately kind of can distinguish between the things you're trying to classify. All right. Now, once you've extracted your features and scaled them and done all that pre-processing stuff, yes, sir.
Yeah. From my experience, I think part of the challenge we have within the security domain is the feature extraction.
Yes.
Because, and I think it's a skill that needs to be learned.
It absolutely is.
Yeah, for example, DGA now, all you probably have is the URL that is auto-generated. Now, from that URL, how do you extract out the necessary feature? What are those things to look at for it?
So that really, the question kind of is, how do you know what features to extract? That really comes down to the data scientist's intuition, and your subject matter expertise. So knowing what features are likely to be predictive of the problem you're trying to solve. Now, with that said, there are some techniques that can be used, such as featureless deep learning, where you can actually pass you can actually use the raw domain without having to extract features. But there's some limitations to what you can do with that, and it's not a panacea of machine learning. But it's something that should be, you should have in your toolkit. There are also some modules out there and some tools that are kind of coming into being that can do automated feature engineering. And I'll show you some of this at the end of the presentation. But really, unfortunately, it kind of comes down to your level of expertise and your subject matter expertise. So oftentimes, if you're not familiar with it, it can be good to, if you're not familiar enough with the problem space, it can be good to pair up with a real subject matter expert, so they can kind of show you what matters and what doesn't. Okay. One of the interesting things also, I'll just throw this out there, is that I know that you can do this in Splunk. I'm reasonably certain that Elasticsearch also has a machine learning interface. So some of this process you can actually do directly in those tools. Okay. Once you've built and trained your model, the final step in the whole process is evaluating the performance of the model. And then usually what happens is it takes a number of tries to get it right, and so you'll repeat this process until you're happy with the performance metrics. Okay. All right. Given the time, we're going to skip that. All right. So I'm a Python person. I do most of my coding in Python. It has a ton of wonderful modules that will make your life a lot easier. I'm a very lazy person. I do not believe in reinventing the wheel. So my advice to anybody is use the modules that are out there. Save yourself tons of debugging time because somebody else already did it for you. So yeah, so we'll go through some of these in the examples that I'll show you. My other piece of advice is read the documentation. Okay, so, all right. So skip a bit here. So what we have to do, again, our problem here is that the problem that you're going to do in the worksheet is you're going to build a model that can identify these potentially malicious domains. What you have to do first, though, is we have to transform this domain into something that a machine learning model can understand. We have to extract features from this. So what we have to do, some features we might want to think about are like the length of the domain, the number of vowels that are present, the number of digits. Things like this can be indicative of potentially malicious activity. So if you think about like most legitimate domains, they will not have a whole lot of numbers in it. In fact, there's very few domains that I can think of that have numbers in them, legitimate ones, aside from like 1-800-Flowers and, there's not that many. Anyway, there are other features that you might want to think about, like the ratio of vowels to consonants, the number of different characters used. Most languages will fall within a certain range of like character diversity, and it's different for every language, so you can kind of predict that. Whether or not it's composed of dictionary words. These are all things that are potentially predictive of whether or not a domain is malicious. Now, what the goal here is you want to come up with a representative set of knowledge that is complex enough to accurately describe the problem. Now, again, this is not, you're not hard coding anything, because what you're doing is extracting these features or attributes every time you pass it a domain. And then that is what is being used to make the classification. All right, now, in this particular problem, again, we can find these, there's different categories of features that we could use. So we could use the lexical features. So again, these are the things that the length, the number of vowels, all that kind of stuff. You could include a blacklist or a whitelist as a feature. Now, there are a lot of like security blacklists and whitelists out there. The problem is that they're virtually instantly out of date the second they're published. So, but it can be useful as a feature, because if you know, like if you have this data, you can include it in your model and it can help make it that much more accurate. You can also look at things like the host, who hosts this domain. So if you can get access to that data, you can find like how long, when it was registered, what registrar it is, all kinds of other attributes of the domain, and those can be used as features. Now, that is a little bit harder to get though, because now you have to pull data from Whois or DNS servers or whatever, and now that's a little bit more challenging to do. And then finally, this other family of features would be content-based. So this would be actually like pulling the website that this URL points to, and getting information about that. That I would not recommend, because you could be potentially pulling back malicious stuff and looking at that, so don't do that. So what we have to do in order to build a model to classify domains is we have to take our original data set and we have to transform it into the data set you see at the bottom there, with our features. And then once we have that, then we can also get rid of the original domain. Now, the features, oftentimes if you look at machine learning tutorials online, you will find the features are referred to as uppercase X, and then the target, or what you're trying to predict, is referred to as lowercase y. I had a computer science professor who would fail you if you wrote crap like that, or if you turned in code like that. So it has been pounded into my head never to write code like that. So I'll spell out features and target and stuff like that. So anyway, and I'm also a code reviewer for Drill, and we would not accept code like that. So one of my pet peeves. Now, once you've extracted your features, then there's a whole other list of things that you might have to do in order to get it ready. So these would be, for example, if you have text, if you have categorical data, the Python doesn't like categorical, the Python machine learning module, Scikitlearn, doesn't like categorical data. So you have to do this step called one-hot encoding, which I'm not going to get into now, but you have to basically do this transformation to categorical data in order to use it. Getting rid of features that are not helpful, encoding strings, scaling features, doing all these things. There's all these pre-processing steps that you might want to think about doing. And yeah, anyway. All right. Dealing with imbalanced data. This is a big issue in cybersecurity, as I mentioned earlier. fortunately, there is a module in Python that will help you deal with this, and it is called Imbalance Learn. And what it does is it provides a whole collection of resampling techniques. So what it does is it...
Go back one, just for a
Oh,
second.
yeah, sure.
Actually, will you be able to have the slides?
Yeah. The slides are available in the GitHub repository. So
Okay.
if you download the GitHub repository, the slides are there.
Good.
So Imbalance Learn, it has many different algorithms that essentially do the same thing. And what it does is it will, let's say you have a class, like you're trying to make predictions and you have two classes, one of which has 100,000 records and the other class has like 20. So what it will do is it will generate new data for the class that has 20 and that looks sort of like the majority class, and so you get a much more balanced data set. And it has a whole bunch of different algorithms that do this. I'm not going to get into them right now, but the code to generate them is very, very simple. You import the module, and this one uses a random oversampler. The one I would recommend trying out as a first step is called SMOTE, S-M-O-T-E, and I don't remember what that stands for. But what you do is you create the object, you then just call this fit resample with your target, your features and your target, and then it will create a resampled data set for you. And so the end results will be much more balanced classes. Excuse me. Any questions about that? Okay.
Yeah, question, sorry.
Oh, yeah.
Does that feature provide then an indication at the end that this is an artificial data point versus, so you can see or compare?
So the question is,
Right, I can see the benefit of being able to compare false
Yeah.
positives on artificial versus correct data points.
okay, so the question is, does the Imbalance Learn provide you with some sort of marker effectively to show you that this data set, these items are generated and this ones are not? It does not. At least as far as I know, it doesn't. So what you could, I would think though that it would not be that difficult to generate some code to do that. And that's actually a really interesting idea. I'm kind of surprised that it doesn't do that. Or, I don't know, I'm curious now. You've tweaked my curiosity. That's
Something to search.
yeah. Okay, so once you've extracted your features, you've done all this, you have all these features, how do you know which features you should use? Should you use all of them?
No.
No! Well, maybe.
You don't have memory.
It's okay, so if you're not going to use it, how do you know which ones to get rid of?
You see it?
So there is an automated way of doing this. The Python module Scikitlearn provides, I believe, it has a few different ways. The ways that I would show you first are called select k-best and select percentile. Both of these work in more or less, they do the same thing in slightly different ways. The select k-best, you tell it how many features you want, and then it will score all of your features, and then it will provide you with that many. So you set k to 10, it will get you your 10 best features. So you have to decide how big of a feature set base you want. The select percentile does more or less the same thing, only you set a percentile and say, I want the, I don't know, whatever percentile of my data, and then it will find the best examples of that. So it does the same thing, slightly different way. Sorry.
Could you explain how a feature gets a score?
So there are several algorithms that it uses to do that. Essentially, it looks at the variance of that. I'll show you some. I'll show you some visualization for that, and you'll see kind of how that works. But there are different algorithms that it uses to do that. And, all right, there is a really great module which I love called Yellowbrick. Has anyone heard of this before? Okay. All right. So Yellowbrick is a Python visualization module that is built for doing machine learning visualization. And I really like this because it can help you. I tend to do better with visualizations, and it helps you find basically the effectiveness of your model and or your features. So this is a covariance ranking of a model's features, and there are 23 features there. And so what you're looking for in this case are features that have a large covariance, either positive or negative. So dark colors are good, light colors in this case are not, and that would be tell you that these features are potentially useful. the code for, and Yellowbrick has a lot of different visualizations like this. This is just one of them. The code for this are all basically the same. So you extract your features in your target, you create the object, and you see the line there that says visualizer equals rank 2D, you pass it your features, you tell it what algorithm to use. Then you call this fit method with your features in your target. You call the, some of them you have to transform, some of them you don't. So that middle line there is dependent on what you're trying to do. And then the final step is you call this poof method, which, as the name implied, poof, your visualization appears. So someone once said that that really should be called ta-da. Now, there is another visualization library which I really like called Seabourn. Does anyone use Seabourn? Okay, more hands go up. Awesome. This is really good. Somebody asked over here, how do you know if your features are any good? This is this pair plot is a Seabourn visualization that I like to use because it can tell you right away whether or not you're kind of on the right track. And what this is doing is it's plotting, it's creating a plot where it's comparing all of these features, and the colors represent the different classes that are here. So when I do this, what I'm looking for is evidence of separability, meaning is there some sort of clean dividing line between the feature set? If there is, that tells me that these are potentially useful features. If these features just look like someone's throwing dots on a plane, then it's probably not a useful feature. So that's what you want to look at. The other thing that's very nice are the distributions that are going along the diagonal. So again, you can see whether or not, like if both colors are distributed kind of evenly, that might not be a very helpful feature, whereas on the other extreme, if you see like the middle one there, where you see the green is totally stacked on the left, and then kind of the blue is kind of tapering off, so that potentially could be useful. Yes, sir?
Would the outliers there indicate that the features might not be good features, or that they are anomalies that are an important feature?
It depends. It totally depends on the problem. But a good question. The question was, do the outliers mean that it's a good feature or not? And it really just depends. Like the outlier could be extremely predictive, or it might just be noise.
So of all the ones that are, sorry, for all the ones that you were showing,
yeah,
would one of those be ruled out, or do you consider all those candidates?
I would kind of like all of these. Just eyeballing. I don't remember what this data set was. So, but I mean, just again, for pretty much every one of these squares, they look pretty, like the dividing line looks pretty clean to me. So, I mean, there's not, this aspect of it, I would say there isn't really like a clean scientific rule about it. Just like, are you seeing dividing lines, or does it really just look like a big mess?
So the lower left hand looks a little bit, but I would think they're all, oh, never mind.
Yeah.
Keep going.
Yeah, no, the lower, like,
even there, it's still clear. It's just
yeah,
you have two blue dots that are below green on the lower left. The rest of them, there's loose clean delineation.
Yeah.
Thank you.
Now, Yellowbrick has another visualizer called a radial visualizer, and this does same basic idea, only it plots it in a radial configuration. And again, what you're looking for is the same thing. You want to see whether or not there's some sort of clean delineation between the features.
Is it based on covariance or what?
This particular one, this is not based on covariance. This is just plotting the features on an XY axis, really. It's plotting more than one of them. Okay. All right. Oops. That was not going to delete that slide. Okay. Now, yeah. So some of this stuff can actually be automated, and there is a really great tool called Feature Tools. What Feature Tools does is if you are working with some sort of time series data, or if you're working with relational data, it can automate the extraction of a lot of very common things. So like, let's say you have some sort of, I don't know, the example that immediately comes to mind would be like tracking stock prices per day. And what you might want to calculate metrics like the minimum price, the maximum price, how many sum of transactions, things like that. Feature Tools is a module that will calculate these kinds of metrics automatically. I'm not a big user of this, but just because I haven't had, like, the kinds of projects that I've worked with haven't really mapped to this kind of stuff. But the person I usually teach with, he has had a lot of good experience with this and highly recommends it. So the essential idea is, again, it will find relationships between data sets, and it will automatically extract a lot of these features for you. So very big time saver there. And, okay, all right. So you've done your feature extraction. You have your data. You're convinced that it's good. What do you do next? Well, the next thing is you actually build the model. So we've extracted our features here. Then what we're going to do first is we're actually going to split our data into training and testing data sets. There's a function that does that, and you'll see that in the worksheet if we get there. We will build the model using the training set, and then we'll evaluate it using the testing data set. When you're doing this for the first few times, it can be confusing when to use what, but you'll definitely get the hang of that. So there are many, many different classification models that you can use. I'm going to highlight 2 of them. But I want to first explain just kind of how they work at a high level. So if we are considering our case of identifying evil domains, we have 2 features here. We have the entropy plotted on the y-axis, and we have the length of the domain plotted on the x-axis. And let's just say that the green dots there, or the green squares are the bad ones, and the blue circles are the legitimate ones. So what the machine learning model does, if I were to ask you this red point here, what would you kind of intuitively suspect that is it? Which class would you suspect that's a member of? Green, right? Any contrarians that say the blue? All right, there's always one of you. Okay, how about now? The blue. Blue. All right. Okay. What about now?
Blue.
Huh?
Blue.
Blue?
Assume it's bad.
Assume it's bad. All right, fair enough. Okay, so this is a little bit harder. So at a high level, when you build a machine learning model, what it does is it will take your data set and it will try to find some sort of dividing line between the classes that you're trying to predict. Now, I should add, the examples I'm showing you all have 2 classes. This can be done with more than 2 classes, but it's easier to think about with 2 classes. So, and the principle is basically the same. So what you were trying to do is you're trying to define what's known as a decision surface. And that decision surface is the boundary between the classes. In real life, there would be more dimensions than 2, but I can't holographically project that, so we're doing 2. Now, if we have something like this, we'll get a very different decision boundary. Now, decision boundaries need not be straight lines. They can be curved, they can be all kinds of weird shapes, and the model will discover that. So that's kind of just the point I want to make sure I make. I'm going to walk through a very simple technique, which is actually quite powerful, and this is called a decision tree. So everybody's probably seen one of these before. And a decision tree is an acyclic graph where you start out at the top of this, and you kind of just walk the graph until you end at, and you cannot go any further. So the example problem here is, well, should I buy a tech gadget? So the first feature we're going to look at is the cost of the tech gadget. So if it's less than $200, then we'll arrive at the yes leaf node there. If it's greater than $200, then we go to the wife's approval feature. And if that is true, then we arrive at a leaf node, and if we arrive at the do not approve, then we arrive at the will she notice feature. And, okay, so yeah, you got the idea. All right. Now, what can happen in a more real context? We might have something that looks like this. So the first feature we'd look at is the entropy. If the entropy is greater than 4, then we know it's, or less than 4 rather, then we know it's malicious. If it's greater than 4, then we look at the length. What happens is, now when you build a decision tree, you're not writing these rules. What happens is you feed the model your data set, and it will discover these rules on its own. And that's kind of how it works. Now, decision trees are a very good technique if you have to explain how your model works to other people, especially non-technical people. Not trying to make light of it. There are many situations where you might be building a model and you have to defend it to an auditor or somebody or a regulator or something like that. And if you are doing that, there are modeling techniques that it's very, very difficult to do that. Not even talking about the math, but it's very difficult to actually say, here's how we went from this raw data to this prediction. And a decision tree is a good one to use because you can actually print it out, you can literally walk them through it and show them how that works. So something to consider. Another technique, which I just want to quickly go through, is a k-nearest neighbors classifier. Who's familiar with this? Awesome. Okay, all right, so basically the way this works is you set a number k. What you then do is you find that many nearest neighbors, and you say, okay, that set of neighbors, which is the dominant class, and then the unknown point is assigned the dominant class. So if we set k is equal to 1 for that unknown point there, the nearest point is the orange point, so the unknown point would be a member of the orange class. If we set k to 5, now we have, looks like, 4 normal and 1 infected, so we would assume this is normal. This technique, it's one of these things that it's so simple, but it's really shocking that it actually works at all, but it can be a very powerful technique, and it can work really well. Especially if your data isn't so linearly, if it's very noisy, this can be a good technique to try out.
Question?
Yes?
Sorry.
Yeah.
Could you explain how the k value relates to the radius of that circle?
Sure. So the k value refers to how many different data points you want to consider in an item's nearest neighbors.
Oh, okay.
So it just find the 5 nearest points to that.
Got it.
And there's an article for further reading about that application for security. Okay, yeah, so the advantage is it's good for the noisy data set, and it's flexible, it's easy to understand, it's explainable. The disadvantage is you have to pick that value of k. The training is very fast, but actually, if you think about why, the predictions are very slow because it has to check, it has to do a lot of iteration. So, yeah, and you have to have a meaningful distance function. Okay, another technique. Now, there are many different techniques for doing classification. However, what people have found is that by combining different techniques in what's called an ensemble, you can get much improved results. And one ensemble, so ensemble learning, it's a process of combining this. You can combine different modeling techniques. So somebody in the back asked, well, how do I know which technique to use? Well, one technique is to try all of them and kind of average their results, or try different collections of them, kind of average the results. But a very popular technique is a technique called random forest. And what this does is creates a collection of decision trees, or a forest, and then it uses the forest's collective prediction as the answer, I guess, that it's trying to predict. I'll let you read kind of how that works, but yeah, if you're ever interviewing for a data science job, one of the questions they always love to ask is, what's random about a random forest? Yeah. If I ever interview you, I promise I won't ask that. What it does is it takes a random sampling of features and builds a subset of suboptimal trees, and then, anyway, all right, not really important right now. Okay, so there are two kind of things that you can, there are two things that you'll want to kind of adjust when you're building a random forest. One of which is the size of the random forest, so the number of trees that it's going to grow, and then the other is the maximum feature, so the size of each tree. And that can have a very large effect on how well the random forest works. I'm showing you random forest because it's one of my favorite algorithms to start out with. It's just very effective in a lot of different situations. And so, yeah, so it's kind of like my starting point for a lot of this. And what you're seeing here is a graph of the error rate and the number of trees that you have in a particular model. So you see what will happen is the error rate will kind of plateau at a certain point, and that's when you the ideal number of trees in a random forest. And likewise for the size of the trees, similar situation. All right, now my clicker stopped working. Awesome. Okay. So, all right. Now, this is a very good technique. It's competitive with some of the best supervised learning techniques. It is less interpretable. It is kind of slower to train and to predict because there's a lot of computation involved. But again, a very powerful technique. Scikitlearn, which is Python's machine learning module, has a lot of different algorithms available to you. These are the same on the rows here represent a single problem, and the columns represent the different algorithms. So what this is showing you is just different decision boundaries that the different modeling techniques can generate. So you can see how your choice of model will radically affect what kind of predictions the model will make. And which one is best is largely a function of what your data looks like. All right, so getting back to our problem, DGA classification. On the left, we have legitimate domains, and on the right, we have suspicious domains. Clearly, these suspicious domains look very different than legitimate ones, right? Yeah, exactly. They look like banging on the keyboard. So, but when you're trying to tackle this problem, if you were doing this from scratch, you would have to kind of sit there and say, okay, I see that there is a distinction between the two. What is it? What captures that? And how can I encode that mathematically so that a model can identify that? And this doesn't really come across very well, but here's an actual decision tree for doing DGA. This is, I said this earlier, this is a very good problem to kind of practice your skills on. First off, because it's really easy to get data for it. The algorithms that generate these have been made public by malware researchers, so you can literally like generate 1 million of these bogus domains, and then there are lists of legitimate domains. So it's very easy to get data. It's also just a very easy problem to understand, and it's a real world problem. Like this is something that kind of real world use. Now, people have solved. There are models that are commercially available that will can identify these kinds of domains with a 99 I think it's like 349% accuracy. So people have developed very, very effective models to defeat this technique. All right, so implementation. Don't worry, we're almost done. Who's done machine learning in Python before? Okay, about half. Yes, sir.
Sorry, before you start, just a question about that.
Yeah.
In the same way that cures for disease will eventually, if it has 99% applicability and will cure the disease, then it's not that you'll continue to see, 1% over time. It will eventually decrease to 0. Is the same sort of thing similar for if we have models that will detect that within 99%? You're no longer seeing, the 100,000 emails to your SOC, that because now this is no longer a functional method for malware producers. Is that a pattern that is seen in your line?
So what tends to happen in security problems is like someone will create some sort of devious way of doing something that they shouldn't, and defenders will eventually figure it out and devise some sort of preventative measure for it. So we'll see like the effectiveness of whatever they're doing drop way down. Then the bad guys will basically say, okay, well, we either need to improve our technique or come up with something else entirely, or just stop doing that because it's not effective. So one of those things will kind of happen. And so what happened was with this problem, what they started doing was, instead of generating domains that look like random gibberish, what they started doing was taking dictionary words and generating them in random combinations. So you might have domains that, instead of looking like a hash, they would look like, I'm just going to look at objects on this table right here. They might look like thermoschairpurse.com or things like that. That becomes a lot harder to detect. So generally what happens is the adversaries get more sophisticated or just try different techniques. You won't. Part of this, though, and part of putting models into production is there's a constant, you can't just put it in production and forget about it. You have to constantly monitor its effectiveness and often retrain it. Because again, the people that are doing this they're looking at how effective they're being, and they're trying to improve also. Yes, ma'am?
How often should you retrain your model?
Your question is how often should you retrain it? That is, again, it's largely a function of what you're trying to do, but I mean, you want to keep an eye on it. And it's not something, but what I would say is, I can't say you should do it always, once a month. That'll work. It really depends on what kind of problem you're trying to solve, and what I would say is, you can't set a definitive time, but you should always keep an eye on it. Sir?
How often from your experience does retraining mean just going through and pumping the data through and confirming the new data there's a change versus, crap, start over?
It's more of I think the former than the latter. It's more of, getting new data, putting it through, checking their performance metrics, seeing if they're staying within your threshold, rather than just like abandoning the whole thing.
So the heavy lifting's up front?
Yeah, the heavy lifting is definitely up front.
Thank you.
Okay, so if you've never done machine learning before, this is probably the good news slide of the night. This is the actual code for doing this. And the good news is that if you've coded in Python, this is very simple to do. Scikit-learn is the module that does this, and it's a very, very well-designed module that's also very well documented. The pattern for implementing any one of the modules, any one of the algorithms that you saw, the first thing you do is you create the actual object, and this is done by just, in this case, random forest classifier, but it would be anything, any one of the algorithms you saw. Then the next step is you call a fit method on that object that you just created. And you pass the fit method your training features and your target set, your training target. Once you've trained your model, then the next step is you call a predict function, and that will get you a list of predictions, which you then compare with the actual values to see how well your model is performing. And so again, this is the same for every modeling technique, and this is the same for classification, regression problems. It's the coding here is very simple. And here's an example. This is a support vector classifier. Again, you see the same pattern: create the object, call fit, and then call predict. And for a random forest, or the decision tree rather, same thing: decision tree, fit, and predict. It's very, very predictable. And this is a list of the algorithm types that are available in Scikit-learn. I would encourage you, don't just like randomly try one of these out. Like, read the documentation for this, understand what kind of model it is before you just start playing with it. Because there's a lot of different features and tuning options that you can use for each one of these. But there are a lot of different models you can try. And oh yes, sir.
Do you have some model and use that model identify which model is the best one?
The question is like, how do you know which model is the best one?
I said, do you have one model?
Oh.
So you use that model identify.
Do I have one model? So, okay. Let me come back to that because that is something I'm actually going to talk. So essentially what a lot of people want to know is, well, how do you know which one to start with? How do you know which one to try? All these kinds of things. When I first started getting to this, I was wondering, well, couldn't you just write a big loop and just try them all out and see what works? And it turns out somebody actually did exactly that. They wrote there's a GitHub repository, I think it's called like the big loop, and it literally will just try every one of these modules out and see which one gets the best scores. Now that is a horribly inefficient way of doing it, and there's a much better way of doing it. So, I will show you the better way of doing it. Okay, this has no audio. Hang on. Oh, wait. Hold on.
Sometimes you don't know if you can trust a machine learning prediction. Take a doctor, for example. They cannot trust a diagnosis just because...
Sorry. Before I start that, I just want to say, one of the challenges also can be understanding how trustworthy the model is. I saw this paper about a year ago, and it's a technique for explaining a prediction that comes out of a machine learning model. So I'll play that.
Sometimes you don't know if you can trust a machine learning prediction.
Turn it up.
Take a doctor, for example.
Put the
They cannot
microphone
trust a
on.
diagnosis just because a computer says so. You also need to know if you can trust the model before putting it into production. Let's say we have a machine learning system that can detect wolves. We can look at accuracy and at some of the predictions, and they may look good. But is that enough for us to really trust the machine learning system? What if you could understand why any classifier is making a prediction? Even incredibly complicated models, such as neural networks, random forests, or SVMs with any kernel. Wouldn't that be cool? It's easier to trust a prediction if we can understand the reasons behind it. Going back to our doctor, if the model told him which symptoms are important, he would trust it. It's also easier to figure out if you shouldn't trust a model. If our wolf detection system is actually just detecting snow in the background, we will not trust it, even if the accuracy is high. I said it would be pretty cool if we could understand any classifier. With Lime, you can. LIME is short for Local Interpretable Model Agnostic Explanation. Let's look at this acronym from the bottom up. We know what explanations are. By model agnostic, we mean that LIME treats the model as a black box, so that it works for any model. Interpretable means that the explanation produced by LIME is simple enough for a human to understand. Finally, local refers to how we get these explanations. LIME approximates the black box model locally, in the neighborhood of the prediction being explained. With LIME, we can explain why a random forest thinks this email is about atheism. It picks up on words such as atheism, or God with lowercase g. It also thinks that God with uppercase G is evidence for Christianity. Or why Google's Inception neural network thinks this image is a guitar or a Labrador. In our experiments, we show that these explanations help real users do all sorts of things, such as choosing between competing models, detecting and improving untrustworthy models, getting insights into the model. LIME helps you finally answer the question, why should I trust you? Thanks for watching. Make sure to check out our paper and open source release. It includes the complete source code and IPython notebook tutorials so that you can explain your own classifier.
Okay. All right, so somebody earlier asked me, like, how do you know if your predictions are any good? So I was holding off on answering that until you saw this. I saw this, I really like this, and this is really this is really no joke. There was an example a while ago. I saw like an article or a blog post about this where somebody, who's heard of Johann Sebastian Bach? Seriously? All right, okay. So he died in 1750. A lot of music that was thought to be written by him, it is doubtful, it is not entirely certain whether or not he wrote it. So somebody wrote this model to like make a prediction on whether or not a particular piece of music was written by Bach. And they got this model and it worked they thought it worked really well, and they were able to predict with what they believed to be very great accuracy that, which was actually written by Bach and which was not. Turns out they were wrong. What the model actually did was it actually discovered that the stuff that they thought was not written by Bach was printed by a different publisher. They used different margins of the paper. And so what the model did was it identified that the quote-unquote legitimate ones had different margins than the illegitimate ones, and it honed in on that feature. And so that was what it was using to determine whether or not it was legitimate or not. So knowing which features are kind of influencing your model can be very, very important, and to determine whether or not your model is actually finding something of value or not. In that case, not. In this case, so here's the code for using this LIME module. And so what you can see here is, okay, so the code is pretty straightforward. You create this explainer, you then just say explain instance, and you pass it a row and your model, and it generates this visualization down at the bottom. But what it's showing you is which features are contributing to the conclusion and in which direction. And so again, it's very, very useful, and so you can really have an understanding of how the model is actually arriving at a conclusion. All right. Related to that is actually assessing your model's performance. So you've built your model, you've done all this stuff. I don't have enough, one of the topics that definitely deserves a lot of attention is how you evaluate model performance, but one of the common tools is a confusion matrix. Scikitlearn has a way of producing these, which is very nice. However, Yellowbrick has a nice visual confusion matrix, which the code for that is right here. I like this because it's color-coded and it's very, very easy to see at a glance how well your model is actually working. So what you want to see is dark red on this direction diagonal and light cream colors on this direction. And if this, you can actually see the numbers so you can see what the percentages are. But if you're not familiar with a confusion matrix, the upper left are the true positives, the lower right are the true negatives, and then the lower left are the false positives, and then the upper right are the false negatives, or perhaps the other way around, but that's the ones going this way are the wrong ones, and the ones going this way are the right ones. So you want more right than wrong. It will also produce this classification report. Now, I apologize, I don't have time to get into what all these classification metrics are, but basically, this will create a visualization for you, and it will generate all of these metrics all at once, so it becomes very easy to assess your model's performance. I really like this. Very useful for comparing different models, because you can see the one on the left here, the random forest classifier, you can just at a glance see that it's performing a lot better than the one on the right. And this follows Yellowbrick's pattern of create the object, fit it, score it, and poof, and then you get these visualizations. All right. Final topic. Okay. So you've seen we can automate selecting features. I didn't really talk about tuning your models too much, but it turns out that you can actually automate just about everything in this process. And yes, I saved this for last for a reason, because it's important to actually understand this. But there is a Python module called Teapot, and there are a few other proprietary tools out there that basically do something very similar. They automate large chunks of the machine learning process. What Teapot does is, if you imagine the whole data science process, we start out with raw data, we clean our data, then we select features, we do this pre-processing, we pick models, we tune the model, and then we output, we're done. Teapot can automate all that stuff in the gray there, which is extremely helpful. Now, there are other tools such as Data Robot, which is a proprietary tool, H2O AI, again, another proprietary tool. Both of those tools work very similarly to this. And Google and probably Facebook, they are working on, they have tools like this as well that some of them they share, some of them they don't.
Microsoft has one.
Microsoft, yeah, pretty much probably everybody's getting this. I'm a big believer, again, I'm a lazy person and I want to, as they say, skate where the puck is going, not where it's been. I was looking at Kaggle competitions, and you start to see that there are more and more automated entries in the top 10s. What that's telling me is that it is not like, if you want to waste your time, not waste your time, I shouldn't be so harsh, that getting into like doing all this stuff manually is not a good use of your time. What is a better use of your time is understanding the problems, getting good at the initial data analysis, the feature extraction, all the stuff that a computer cannot do because it just, at a fundamental level, it doesn't really understand what it's, in the same way the human does. So a lot of these steps can be automated is the bottom line here. Now, I've tried Teapot. I tried it with some relatively simple Kaggle competitions. Again, it didn't get me in first place, but it definitely within the top 10. It will. I mean, I don't do Kaggle competitions, but I mean, like, I looked at past ones and because I wanted to see how well it did, and it does pretty well. It is bloody slow, so you have to have a powerful computer and you have to have a lot of patience because there's a lot of computation. But it does this intelligently. And I would definitely encourage you to try it out. The code for this is also very, very simple. You import the object, you create the classifier or regressor. The tuning parameters there are kind of more of just a limit of like how much you want it to run, like how long you want it to run. You call fit and then score, and then you can actually, what's really cool about Teapot is it will export executable Python code for you. So it will build this model, train it, and output code for you if you want. Very, very slick. Yeah, and so the documentation is there. Now, I talked too much, so are there any questions?
Could you put the GitHub again?
Which GitHub?
Your presentation.
Okay, yeah, sure. That was an easy one. All right, other questions now.
How do you find out about these packages? Like, I wouldn't know that this thing existed if I had come here.
So I have no life, and I read a lot, and just I'm constantly looking for stuff like this. But my belief is a lot of those steps again that are automated or can be automated. A lot of the mathematics that go behind machine learning can and will eventually, in my view, be automated. So my view is that if you want to really become effective at this, again, focus your energy on the things that will not be automated or cannot be automated. So. Yeah, let's see, I'll come back, I'll kind of go around this way. Sir?
So are you able to see like, oh, the teapot decided to use this ensemble with this, and this?
Yes.
Okay.
Yeah. You then, you.
Considering that you were talking about you had to sample down your data and that, over time you might have to retrain, it could be changed, how important would you consider cross-validation in that process?
Consolidation?
Cross-validation?
Oh, extremely. Extremely important. Sir?
Has the ease of using deep learning kind of reduced the importance of some of the classical machine learning models?
So the question is, has the ease of deep learning reduced the importance of that? I would say no. Here's why. I think while deep learning is definitely getting easier and more accessible, it still requires a lot of data, and there's certain problems that it just doesn't work well with. So I think I see where you're going, and I agree with you. I think it's going to get easier and easier to use, and there's going to be more and more applications for it. I still think there's definitely a case for what I would call classical machine learning. And the reason also is sometimes you just need a simple solution. You don't need to do all the, even though it's simple for the programmer to write, it's not computationally simple, and you end up, it's still very complex to build an effective deep learning model, even though a lot of it is going to be automated. So that's my personal opinion. Others may disagree. Sir?
How does the reinforcement learning adapt in the random forest? Reinforcement learning.
How does it work with?
Can be adapted in a random forest.
I am not sure.
Okay, and the other one is like in BQML, BigQuery ML, we have the query, and directly you can call any of the model directly in the data SQL.
Oh, very cool.
And it does the auto tuning of the hyper variables.
Nice.
So, is that anything in Python?
Yes. Yeah. So I didn't really. When you create a model, I showed you a very simple way of doing this. When you create a model, there are many, many tuning parameters. Scikitlearn provides a number of different ways of tuning those tuning parameters. And actually, there is a workshop. Jason, what time are we supposed to be done?
Around 8:30, 8:45. You got a couple more minutes. Keep on going.
All right. So in the GitHub repository, there is a worksheet. In the worksheet, it's actually the exact question you're asking. It shows you how to tune a model and get better performance out of it via a few automated methods. I showed you the most simple ones in the notebook, which are what's called grid search and random search. There are more sophisticated ones that are available as well that essentially use machine learning to tune machine learning models. Sir, there was a question over there.
I'll ask you.
Okay, cool. Sir.
So when you create your machine learning models, you have your training set and your knowns and testing.
Yes.
Everything's known. Is it particularly useful to take results from a model that you deem to be good and use the results of this is good, this is bad to refine the model, or is that getting closer to like the deep learning where it tries to kind of teach itself? So if you had like a large set of data,
Yes.
and then you use live data
Right.
that then gives you good and bad results.
I'm not entirely. I would think it would be probably good to do that. I'm not entirely sure. Yeah, I would think it would be, sir.
So after you did the classification of that, you found map, then what happened?
Then what happens? The question is, what do you do once you find something?
No, I mean for the what you doing?
The DGA?
Right.
Well, so in that case, if I was building a DGA, in real life, a DGA classifier, it would probably be sitting on some sort of data stream that was coming in from like a firewall or from a router or some sort of network device. So what I would want it to do is I would want it to then send some alert if it finds something. And send basically the information that, the details of that to someone who's going to respond to that incident or basically take some sort of action. Now, of course, a better situation is if that could be automated as well. So you have kind of this automated incident response, and there are tools that can enable that. Sir.
Earlier on in the presentation, you mentioned the tool that basically specifies domains if they're legit or non-legit.
Yes.
And that got me thinking: is there an easy way to tell if that kind of technology is integrated into like commercial tools? Because that's one of the biggest challenges that I've had is everyone advertises they use machine learning, but sometimes it's just a SQL query.
Yeah. So the question is, how do you distinguish between like actual machine learning and rule-based? Oftentimes you kind of just have to like kind of interrogate the vendors a bit and see what they're doing. And even when they say that they're using advanced AI or machine learning or whatever buzzword exists this week, you kind of have to like press them a little bit about it. And what I would suggest, I would strongly suggest becoming familiar with how machine learning models are evaluated, and when someone is trying to sell you a product, really press the vendor on those performance metrics to see to what extent they'll tell you that. And that'll tell you if they're serious or not, because if they are, they'll have no problem telling you that, and B, you'll get a sense of whether or not the product's any good. F1 score is one I like to ask. And it's like, I'm not trying to be a jerk about it when I'm doing that. It's like, I really want to see, if someone has something that's really good, I want to know about it, because it can be a major time saver. And likewise, if someone has something that's not so good, I don't want it. Sorry.
Maybe a little out of bounds, but reverse engineering?
Yes.
Thoughts on when you find a model that's attractive, but it's not, you don't have access to how they did it or what?
It's funny you should ask that. It's something that's of great interest to me, actually, is that I read some papers last year about essentially hacking models, like getting them to deliberately misclassify things, which can have some very serious security implications. If you think about, consider that people are developing cars that can drive themselves basically on the basis of machine learning models. Well, there were some studies that were done that convinced very, very sophisticated image recognition algorithms that stop signs were in fact speed limit signs. And so understanding how the model works is totally possible to manipulate them. And so I don't know that you can take a model and completely reverse engineer it, but I would suspect that people are probably trying to do that. And it could potentially be very useful to know that.
I guess the most important thing would be to get the data.
Yeah.
That they used or not?
So if you can get if you can actually get the quote unquote binary of the model, then it's like game over. But if you can get the outputs of the model and you could just essentially feed it different things and see how it predicts, you could start to kind of reverse engineer it that way. I don't know, that's an interesting question. I've often wondered about that. Could you reverse engineer a model and without peering at source code? I'm especially curious because I'm part of a group that does an annual cyber AI challenge, and that actually is an interesting exercise. I'm kind of considering. Okay, so another shameless pitch. I'm part of it. If anyone's interested in a cyber AI challenge, come talk to me after, as competing in it. Come talk to me or email me about it. I don't want to get anyway. Yeah. All right. Okay, so I didn't get a chance for you guys to do this, but if you are interested, let me just pull this up and I can just show you this real quick. There is a worksheet if you want to try your hand at this problem. Now this is in, oh, no it's not. Okay, this notebook, along with the answers, is in the GitHub repository that I prepared for this workshop. Maybe, Jason, could we email that to everybody at the end of this?
Yeah, so I'll put it up on the meetup page and everything.
Perfect.
It'll be available.
Perfect. So if you want to try this out, there's this worksheet. I'm giving you a data set with 5 or 6 features because I didn't really get into feature extraction here. So I'm giving you a data set with these features. And so what the worksheet does is it walks you through the process of creating a model, and then it walks you through the process of improving that model's performance via some automated tuning techniques. And then what happens is, so it does that, it does some visualization. it asks you to compare model A with model B, and then the final step is trying Teapot out and seeing how that goes. So yeah, and so that's the model, and like I said, the answers are also available in the aptly named Answers notebook. So if you want to see how at least how I did it, you can try that out. The Teapot really will run for a long time, so I'm not going to run it now. But welcome to try that out, and please email me any questions or comments you may have about it. So first of all, thank you very much, everybody, for your attention. If you have any questions, I'll be up here for a while. My final thing is, if this topic interests you, I am running a class in May, and if you'd like more information about that, it's in the slideshow on the repo, and feel free to contact me about it. So thank you very much, and I hope you enjoyed the presentation.
Well, thank you for coming. All I ask is if you could just clean up after yourself, and if you asked a question, you can go up and get a prize. Thank you.